Hello everyone, myself Dr. Ranjana Gogoi of Department of Statistics, Gorgaon College. Today I am going to discuss about the hypothesis testing of the regression parameters beta of the multiple linear regression model. This lecture is based on the syllabus of BSc CBCS 4th semester statistics honors paper linear models taught in the colleges under Dibrugarh University. Here, we consider the testing of hypothesis and confidence intervals for the parameters beta naught, beta 1 up to beta k in the multiple linear regression model. This is in matrix form y equal to x beta plus epsilon. So we know that to estimate the parameters of the regression model by the method of ordinary least squares, it does not require any assumption about the probability distribution of the disturbances epsilon I and as well as the yi. So to derive significance test and confidence intervals for the beta I cap, we may proceed by assuming that epsilon I is to be normally distributed, and in compact form we may write it as epsilon follows normal distribution with mean 0 and variance sigma square I, and that is In is the n by n identity matrix. So it follows that the likelihood for the n sample values will be L is equal to 1 by twice pi sigma squared to the power n by 2. As epsilon follows normal distribution, so likelihood will be based on the normal distribution. So it is exponential minus epsilon prime epsilon by twice sigma square, which is equal to 1 by twice pi sigma square n by 2 to the power n by 2 exponential minus y minus x beta prime y minus x beta by twice sigma square. So the maximizing the likelihood with respect to beta, this is equivalent to choosing beta to minimize the sum of squares y minus x beta prime y minus x beta. This is exactly the least square criterion already set up, and so the maximum likelihood estimator of beta is simply the least squares estimators already obtained, that is beta cap is equal to x prime x inverse x prime y. So this parameter estimate beta cap, that is actually the ordinary least square estimators of the regression coefficient, itself is normally distributed with mean equal to true parameter beta and the variance sigma square x prime x inverse. So thus beta cap follows normal distribution with mean beta and variance sigma square x prime x inverse. So if sigma square was known, this result would enable us to carry out the test of significance and estimated confidence interval for beta. But sigma square is not known, so we take the unbiased estimate of sigma square, which is nothing but small a square is equal to 1 by n minus k minus 1 into y minus x beta prime beta cap prime y minus x beta cap, and which is after simplification, it is nothing but y prime y minus beta cap prime x prime y divided by n minus k minus 1. That is, the s square is equal to sums of squares due to error divided by n minus k minus 1. So then, beta cap and sigma square have the following properties, which enables us to use the t distribution to derive tests for individual regression coefficient. The properties are, so beta I cap follows normal distribution with mean beta I and variance AII sigma square. Here this AII is the ith diagonal elements of x prime x inverse, and summation I from 1 to n epsilon I square by sigma square. This is, it follows a chi-square distribution with n minus k degrees of freedom. Hence, from the definition of t distribution, t is equal to beta I cap minus beta I. This is the estimated value, this is the parameter, divided by square root of summation I from 1 to n epsilon I square by n minus k into square root of a. This t has the t distribution with n minus k degrees of freedom, where aii is the ith diagonal elements of x prime x inverse. So to test any particular hypothesis about beta I, we substitute the hypothetical value of beta I here. Here we can put the hypothetical value of beta I, and if the resultant value of t lies in an appropriate critical region, we reject the hypothesis under test. And from there, we can construct a confidence interval, that is 100 into 1 minus alpha % confidence interval for beta I as beta I cap plus minus t alpha by 2 into square root of summation I from 1 to n epsilon I square by n minus k into square root of ai. This is the 100 into 1 minus alpha % confidence interval for beta I. Similarly, we can construct a confidence interval for all betas I from 1 to 3 up 0, 1 to 3 up to k. So now to test the overall significance of multiple regression, we proceed as follows. For the k variable regression model, yi is equal to this one, beta naught plus beta 1 xi1 up to beta k xik plus epsilon I for all I. Then null hypothesis be that h naught is equal to beta 1 equal to beta 2 up to beta k equal to 0. That is, all the slope coefficients are simultaneously equal to 0. Then the test statistics become f. F is the ratio of r square by k minus 1 and 1 minus r square by n minus k. Here, what is r square? R square is equal to beta prime x prime y by y prime y. And the statistic f follows f distribution with k minus 1 and minus k degrees of freedom in an appropriate critical region. Here, r square is called the coefficient of determination. When r square is equal to 0, f is equal to 0. The larger the value of r square, the greater the value of f. So, in the limiting form, r square is equal to 1. If r square is equal to 1, then f is infinite. Thus, the f test, which is a measure of the overall significance of the estimated regression, is also a test of significance for r square. So, in other words, the testing the null hypothesis 1 is equivalent to testing the null hypothesis that the population regression coefficient, that is the coefficient of determination, r square is 0. So, dear student, I conclude today's lecture here. Thank you.